Hello, everyone, and welcome to our podcast. What happens if everything that you thought about was true? All the foundational things in your life were false. Well, today we're going to talk about that, and we're going to take an interesting path to answer that question because we're going to talk about it, how math can give us a roadmap to be able to identify what foundational things are true. Because if we want to know what is true, we need to have some sort of landscape in order to identify truth. We could think about our feelings, but we know our feelings aren't always reliable. So we're going to use math as a roadmap to identify what are the foundational things that are true. And I'm super happy to have two people to join me today. We've got my friend Brian Reiner and my other friend Charles Johnson, who are here in Des Moines, Iowa. And Brian, why don't you introduce yourself?
Yeah, I kind of have an eclectic background. I was an actuary for a number of years, and that's where Dave and I met. We're actuary in early 90s, I think, 1990s, not 1890s. We're not that old. But eventually went to seminary and became a pastor, and that's what I do now. So I kind of look at things. I took some philosophy classes too, so I try to look at things a little bit from a theological and a philosophical way, even though I still have some math geekdom in my blood. So I can.
Is that a word, geekdom?
Yes, it is now. But I think that's kind of where I come at things, and so. Over the years, and I think with Charlie, you and I met a couple years ago.
Yeah.
And so we've just kind of developed this friendship together from different cities, but that's where I come from, as far as looking at things from a little bit more of a metaphysical or I suppose theological viewpoint. And that's kind of what I'll try to bring to the conversation anyway.
I'm Charles Johnson, also a former actuary, mathematician, and I'm very much a physicalist and agnostic, but I find the history of both mathematics and humanity intertwined in a way that is very worth studying. And so that's what we'll pursue today. We'll try to understand how these historical foundations of math and reasoning and human understanding have evolved over time to get us where we are today, with the hopes that understanding that history can help give us guideposts for navigating the future and discovering new truths.
Mm-hmm. And quite honestly, my background has been such that foundations of my life have been rocked. And, if you live as long as I have, I guess that's probably going to happen a couple times. And this happened to me within the last 5 years. And the stories that we're talking about today really were key for me to get to a better foundation, to get that more solid, and really gave me hope for a better future. And so that's kind of like why I'm passionate about what we're talking about. It's not just information, it's not just history, but it's something that has proved very foundational to me. And as I've talked with Brian and Charlie about this, we just had a lot of fun talking about it. And we hope to kind of capture that fun in what we're doing. So we're going to cover a lot of time. And we're going to start way back. The math that we're going to focus on is the Pythagorean theorem. And most of you probably think that started with Pythagoras around 500 BC. But actually, it went much further back than that. It went back to the Babylonians, the Egyptians, literally the Chinese. Hundreds and thousands of years before that, there's records proving that they knew about the Pythagorean theorem was true. 3 squared plus 4 squared equals 5 squared. So that truth has been around a long time. Now, when it was actually proved as a theorem, that's a little bit more debatable, and that's kind of like where the Greeks came in. But we're talking about something that's extremely foundational in the world of math. And I'm sure you guys remember studying that in high school, probably.
Mm-hmm.
So, yeah, we're going to go way back to that. And so let's start with what the foundation is of Euclid geometry. So that's the geometry you studied in college, named after Euclid. And Euclid is the one that started his geometry with basically 5 postulates. So his foundation for truth was essentially 5 things, and 4 of those things were very simple and easy to explain, and very intuitive. But then the 5th one was different.
Mm-hmm.
And that's where a lot of controversy occurred. And if you don't think controversy occurs in math, maybe that's one thing you can take away from this, is that this has been one of the most controversial topics in the history of math, is what is this parallel postulate? So that's the 5th postulate. And essentially he says that all parallel lines do not meet, and that is what he was assuming for the Euclid geometry. And so everything that you studied in that geometry assumed that parallel lines do not meet. So do parallel lines meet?
Apparently sometimes.
Charlie's a wise man. Like, let's not answer that definitive yet.
Well, and does he give as a definition, is that parallel means lines don't meet?
Yeah.
So,
so taking a step back, a postulate is just something that, in a proof you accept as true without questioning it.
Correct.
It's there's no basis for it.
Right.
So there's no reason why you pick those things. You simply are trying to prove things.
Yeah.
And you need to have some base starting assumption. You
Yes.
can't, it's, to our knowledge, we can't start from nothing. There
Right.
has to be some genesis
Yes.
of foundation. And in mathematics, the goal is to get the lowest number of base assumptions.
Right.
Okay.
Get it as at the least number of things we have to take and prove as much as we can from
Yes.
these base assumptions.
Right.
And so this 5th postulate in Euclid, and I just want to provide some big historical context. Egyptians used Pythagorean theorem,
Mm-hmm.
right? They
Right.
obviously knew they were
Applied
cutting.
it.
Yeah, they applied it effectively to create massive scale. So we know that this understanding of right triangles and their usefulness and their ability to create them had existed for a long time. And the Pythagoreans and the Chinese, there are different cultures that seem to have proved the single, that not just a 3, 4, 5, but all triangles satisfying this kind of algebraic, this relationship between side lengths. But what happened for Euclid was Alexander the Great. I mean, that's really the foundation of Euclid's book, is
Mhm.
Alexander the Great comes along and decides, I'm going to go conquer the Mediterranean. I'm going to make it a single unified culture. I'm going to name a bunch of cities, after me. And after, Alexander, he conquers and he dies, this Hellenistic age happens. And for, one of the first times in history, there's a really big exchange of ideas and culture commercially and intellectually. And, as we go through the podcast today, that's going to be like, it's this discussion of different cultures and ideas. And in this Hellenistic age, this kind of golden age of information, Euclid has access to all of this mathematical information, and he has the resources in place to transcribe all of it into a book. So Euclid's in Egypt, in one of like the many cities named Alexandria.
Right. Yeah.
And he decides, I am going to try to demonstrate in a concise text all this disparate mathematical knowledge we have.
Right.
And he starts off with the 5 postulates. And that 5th postulate, just for whatever reason, every mathematician after him goes, it's a really convoluted postulate.
Right.
I mean, how do we get rid of it?
Yeah. We want to prove it.
We want to
Or
prove
disprove it.
Yeah, so we can take it out.
Yes.
Right. So then we only have 4 postulates.
Right.
And what an incredible achievement in mathematics
Right.
it would be. And it
Yeah.
took thousands of years to
Yeah.
resolve the importance of the 5th postulate and the implications of it.
Yeah, and I'm going to take a step back. So, I'm glad you brought that up, because Pythagoras himself was really at an age where he started that pursuit of truth, and he traveled all around his area, which was, quite rare at that time, in search of knowledge. And he was privileged. He came from a family that allowed him to do that. And so as he was traveling around, he actually educated himself and then became kind of like this source of truth. People followed him like a cult, like people say, like people followed Jesus. People followed Pythagoras. They ate with him. They had rituals. They communed with him.
So it had a religious.
It was a very
connotation
religious,
almost.
yeah.
Okay.
Yeah. And then the idea of the postulates, I've heard that our country is founded on the concept of what Euclid was trying to do with the five postulates when he talked about in America that there are certain things that are self-evident.
Okay.
And so that's what our country was founded on, like freedom, self-evident. So that's what Euclid was talking about. There are certain things that are true, self-evident. And so that's where that came from. And so, and Euclid wasn't the one that like came up with a lot of the math, as Charlie said. He was the one that kind of like took a bunch of great math and put it together.
Okay.
And so, there's some of you that maybe are great mathematicians and others are really great at organizing other people's work. And Euclid was probably more the organizer. And we need more of those people in our world that can take other people's work and make sense of it. Mm-hmm. So anyway, so there's Euclid. And that a book that he wrote, The Elements, goes through, it's 13 books, goes through a lot of math, cool math. And they say it's the number 2 most read book throughout antiquity next to the Bible.
Oh, wow.
And most copied. And so this is a big thing that's impacted culture. And everyone assumed that everything that Euclid did was right, and is amazing things that he did. Now, there's been a few minor things that they've kind of tweaked over the years, but nothing foundational. And math went on its merry way. And if you think about all the mathematicians from Euclid throughout the years, I mean, there's a lot of people that have studied Euclid. And one of the things that grew from Euclidean geometry as the foundation was trigonometry. So now that's that second area of math that was built on geometry, because the foundation of trigonometry is the trig identity, sine squared plus cosine squared equals 1. And that kind of sounds familiar if we think about the Pythagorean theorem, right?
Yeah.
Because that's a squared plus b squared equals c squared. I suppose we ought to mention that. And so sine squared, if you let that be a, cosine squared, so cosine be b, and then 1 squared is 1. So trigonometry, that theorem assumes that the Pythagorean theorem is true. So trigonometry is built on sine squared plus cosine squared equals 1. And that formula is based on the Pythagorean theorem being true. And it's been thought that way for a long time, a very long time. And so I like to study this stuff. So I've got this book. It's called The Pythagorean Proposition. And it's been written and rewritten over the years, but it started and written in 1907 is when the manuscript was written. Then it was printed in 1927, a second copy in 1940, and then a third copy in 1968, and then a second printing in 1972. And it literally goes through and it just categorizes in a systematic way the kinds of proofs that are out there. So there may be 2 proofs that look different, but then they'll say, well, really, these are just the same proof, just kind of massaged differently. And so he goes through and talks about the different kinds of proofs. There's the algebraic proof, a squared plus b squared equals c squared. That's an algebra statement. And he said that there's an unlimited number of algebra proofs, because we can really kind of like rewrite algebra an unlimited number of ways, but he's breaking them down into a smaller number. And then there's geometric proofs. And again, some people think there's thousands of geometric proofs. He comes down and shows about, I think like 15 or so different pictures that all geometric proofs go by. And then there's vector proofs. And so he categorized all these kinds of proofs as to the different ways at arriving at the truth, which, take a step back. I mean, how cool is that? Algebra, geometry, vectors, all these different ways. And within each one of those, you can look at it differently. And I'm just amazed that, because a squared plus b squared equals c squared in a triangle is not an intuitive idea. I mean, I just can't look at it and say, oh yeah, obviously that's true. It's not intuitive. One thing I think that it's easy to overlook is that it's a formula about the length of the hypotenuse of a right triangle. So A and B are the legs, they meet at a right angle. C is the hypotenuse. So this tells you the distance of C. So it's a distance formula, but it's given to us in terms of area because it's squared. So like if you have a square, you say squared, a squared foot. So right away, it's kind of very cool that the way we get into the distance formula is by using area. And that's how Euclid proved it. He literally used area to calculate it. And we don't think about that. We often think about just in terms of about an algebra statement, but the cool proofs of it really focus in on the area. So, I mean, let's celebrate that a little bit, how really unintuitive and cool this is. And yet we can see it from all these different ways. And nobody's trying to disprove it as being false. We just find new ways of seeing it true.
So is this book more, I mean, which way does it go? Is it say, hey, over the years, these are different ways people came to the same conclusion? Or is it, okay, we know the truth, and these are different ways to show that it's true?
It's essentially saying, it's a little bit both. It goes through the history, but it's saying it's true, and it encourages us to find new ways.
Okay.
He says there's more proofs out there. And there have been, since this book's been last printed, there's been new proofs found. But he came to the topic of trigonometry, and he said there are no proofs in trigonometry. And the reason why is for the reason we just stated, is that the whole idea of trigonometry is based on sine squared plus cosine squared equals 1, and that is based on the Pythagorean theorem. So yes, you could prove it using trigonometry, but it's really just the foundation is.
So it's kind of your proofs are always going to be circular.
Yeah, right.
And then that's kind of a pun, I guess, isn't it?
Right. Yeah. It's circular, but no, it's a triangle. And so here's this book, and this is like a very geeky math book. And like I say, it's been printed. It's last printed by the National Council of Teachers of Mathematics. And so if there ever was like a book that was like almost the Bible of the Pythagorean theorem, this is it. And it's celebrated. And in this book, the author, a very smart, renowned mathematician, says that there's no trigonometric proofs. Now, if you're a math person, you should rarely ever say nothing can happen. You may be able to prove something's wrong. And ironically, in March of 2023, two seniors from the School of St. Mary's Academy, New Orleans in the U.S., and I'm going to try to get their names right, Calcia Johnson and Nakia Jackson, so high school seniors, proved the Pythagorean theorem was true using trigonometry and not by assuming sine squared plus cosine squared equals 1. And so from Pythagoras to Euclid to Newton and Euler and all these mathematicians that were ahead of them, nobody saw this. And to the point where a renowned mathematician says it's not possible. It can't be done. And two high schoolers did it.
Yeah.
I mean, how cool is that? I just love that story because to me that pictures math as not just this stuffy cathedral for people smarter than us to discover new things. It's for everyday average people who are willing to ask questions and explore.
Well, and it got to the point where, like you said, the stuffy part, it got to the point where we know this so well, let's not really do any more research on it because what are you going to learn? We already know this is true. We've got lots of proofs, there's no other way to look at it. We don't need to look at this from a different perspective, which I think when you talk about, like you were going back to Alexander the Great, when you talk about history, you see that in history a lot where people get to the point, well, we think we have the truths that matter. And so then we don't really explore it anymore. We don't look for more ways to find truth. And I think, so that's kind of a good allegory of that. But one thing I didn't know if you knew that, did you know how Alexander the Great and Winnie the Pooh are connected? They both have the same middle name.
So, Brian, what do you do with your time?
I just thought,
So what is
you
the-
want to know that.
Oh, Winnie the
Pooh and
Alexander. I was waiting for what is the name. It's like
that's a little different perspective than you might have thought,
Yeah.
but I think,
that's profound.
well, it is, but I know, Charles, you like the history part, and I thought this is cool. You put in Alexander the Great because he's such a, just a figure that just stands out in history in so many ways. Obviously, an unbelievably tactical military person. But I thought maybe you might want to talk a little bit about the history of the different perspectives of just the thought about even in philosophy and then you've got kind of a psychology background too. If you wanted to give a little bit about that, because I never really, when we talked about this even around breakfast this morning, I never really thought about the idea that this book that you're using as a springboard is a way to something that we think we know is true, but we're looking at from so many different perspectives. And I wonder if we're going to find out that there's some type of math that starts to put this into question,
Yeah, well, so the first thing I'll say is when we look at history, one of the things I think we tend to do poorly is we see things as inevitable, right? Like that because history happened a certain way, that was the inevitability, right? Like Isaac was always going to discover calculus. Alexander the Great was always going to, Euclid was always, but really the most of these things, these discoveries that happened were a result of the context that they happened in, right? Like if Euclid was born at a different time or a different place and the resources were different, like it's unlikely he would have been able to do this. If the requisite mathematical knowledge wasn't there, he wasn't going to be able to compile it. And it's actually something we consistently see, this idea that, we tend to see large leaps in human knowledge and understanding. It's not a linear progression. It's not we slowly and incrementally prod forward. It's kind of this lumpy, we regress, we accelerate super quickly. And, we'll probably talk a bit about that history of math today, but very kind of strangely, they seem to be bunched up in this explosion forward of understanding. And the reason I like psychology and history tying together is I think about that human context of like, why did this individual have that opportunity? Why did this individual progress in the way that they did? And most of it is for reasons that are societal and contextual and not necessarily against the odds. They managed to discover this stuff. There are examples of that as well.
Well, and I think you look at, as you were talking about Alexander the Great, I just had read something recently about how he died. It was some sort of illness that they didn't, and from what I understood, it was actually, even at the time, probably curable, but it was misdiagnosed.
Oh, didn't he get drunk and like pass out?
Well, but he had some sort of, I thought it was some sort of intestinal thing, but I started thinking about this, how much, because we're talking about a time period, BC, and how advanced civilizations were mathematically, but how kind of backward they were when it came to like medicine. I mean, you look at that, if we would have had antibiotics, because what Alexander the Great died when he was 33, I think. What if he'd have lived to be 93? What would we have gotten from him 60 years later? I mean, who knows? I mean, I don't know the answer to that, but probably some pretty cool stuff. He might have, or maybe it would have been horrible. I guess I don't know. But that's the thing. It's like, like you said, history, we think, well, it's inevitable, but that was just one. We talked about that a little bit at breakfast this morning about, how you might meet somebody. Well, sometimes it's just one little thing that changes. But again, what's the thread that comes through this is, are people looking for meaning, purpose, truth, value, all those types of things. And then you just do it in the context that you're in, and so I thought about that. Well, if Alexander the Great would have lived longer, or, if Pythagoreans weren't so religiously goofy, more could have come from it, but they turned it into a cult. and it actually kind of got backward for a while. They had some
Mhm.
really weird beliefs metaphysically.
They did.
Yeah.
Mhm.
And I think that's, I think that, as we talk about the history of a timeline, we're in the negative side now, the BC, you see things line up like that, like you said. You can't always make a direct correlation,
Mhm.
but here I think I like the one you made with Alexander the Great. Could have any of this have happened if you didn't have, the freedom? Well, I think about from a theological standpoint.
Yeah.
You've got Rome makes all these roads,
Mhm.
and then the Apostle Paul is able to talk about, Jesus
Mhm.
because he can go on these roads. He
Mhm.
didn't make the roads,
Mhm.
Yeah.
but it was a good timing. Yeah.
Okay, this is totally unrelated. I have a theological question. So Paul is originally Saul,
Right.
right? And he
Right.
worked for the Roman government.
He was a Pharisee.
Yeah, he was prosecuting people who were
Yeah,
For the
persecuting-
Jewish government or for the
Right.
Jewish leadership.
yeah,
right.
but that's his job was to go root out
Oh yeah.
Kill
heretics.
Christians.
Yeah.
Yeah. Well, Christians or any other
Mhm.
religious,
Right.
Anything
popping
that's
up.
going against Torah
Yeah.
that he thought. Yeah.
So, is he also the only apostle who lived like his full life? Didn't all the rest of them get executed for preaching Jesus' name? I mean, I don't know if he was, but he lived a really long time.
Yeah. Sean McDowell wrote a dissertation on this.
Yeah.
And he just came out with a new book that, and if I remember right, it's called, I can't remember what exact the book is called, but it's like The Fate of the Apostles or something
Yeah,
like that.
yeah.
And for years, people would use this postulate that one of the reasons we can believe that Christianity is true is because people were willing to die for it.
Yeah.
Which I think has some weight, but it doesn't take a theologian to figure out, well, there's maybe some problems with that. But what he found out is we're historically pretty darn sure that 4 of them, including Paul,
Mm-hmm.
were martyred.
Mm-hmm.
Out of the 12, well, that would be 13 or 14 because
Yeah.
Paul's kind of added on. But there's another 3 that we're kind of sure,
Mhm.
and then the rest of them we don't have a clue.
Oh,
It's
really?
more traditional.
Okay.
And so we have a couple within the text.
Yeah.
James and Stephen. But I think back to your question. They all
Did
think.
Paul live a long time? I guess
Paul lived quite a while. If we figure that he's similar to Jesus' age,
like
so
20s, 30s. Yeah.
we think he died in 68, 69 under Nero.
Okay.
So
So it was 70. So I thought it was just very interesting that he, as someone who previously persecuted heretics, essentially became someone who adopted a heretic religion.
Mhm.
And what I thought was curious is like, I wonder how much his education about heresy prosecution allowed him to be so successful.
Mhm.
To navigate, I know how not to get caught because I know how they work and identify them, and
Yeah.
and I know how to push the boundaries without
Mhm.
going so far that they're going to come chase me down
Mhm.
in a way that allowed him to like incrementally
Mhm.
because I think about that a lot. Jesus was around for a relatively short period of time in his life,
Mhm.
right?
Yeah,
Like
yeah.
I mean, it was not very long.
Like 3 years. Yeah.
And so a lot of the progression forward is one in the context of the Roman Empire, right? There was a connectedness to the world. And bringing this back to Euclid wasn't Egyptian.
No.
He was Greek.
Mhm.
He left his home,
Mhm.
traveled all the way around the Mediterranean
Mhm.
to this, Egyptian civilization in
Mhm.
Cairo and Alexandria, and had a giant library of
Mhm.
information from cities all over, and used that to create something that then could be disseminated. And so I was thinking about that in Jesus's time, like how much the connectedness of the Roman Empire, and then specifically who are the people who carried on his information afterwards, and why did that specific subset of religions become the global dominant religion over the next thousands of years later?
Mhm.
It's a very interesting story.
It is,
Right.
and it does come back to this in a sense that there is kind of, they're allegorical to each other, I
Mhm.
think, and it's so cool to see how little things work into bigger things, but it kind of comes back to what you were talking about, Dave, with the truth. It seems like and I think we know this, that something about the human psyche that we just you don't really have to be taught that you should look for truth.
Mm-hmm.
It's just something we just do.
Mhm.
And I think that's different than any other species, really. I
Mhm.
mean, not the way we do,
Mhm.
not the way we look at it. And, you know, you look at it, you know, I don't think, a porpoise is going to look at this and say, oh, this is cool.
Mhm.
You know, I mean, even though they have some intelligence,
Mhm.
but I think it's just that there's something within us
Mhm.
in whatever worldview we're looking at,
Mhm.
you know.
What comes to mind is my son's 2, and for the last like 2 months he's been in the why phase, and just how universal that is in your childhood of why.
Mhm.
And I think that really gets at our pursuit of truth.
Mhm.
We want to know why
Right.
things are the way they are.
Right.
And I think harvesting and leaning into that childish curiosity and open-mindedness of why things are the way they are, so that we can help explain and then navigate the world we live in.
Mhm.
Yeah.
One of the things that to me is one of the saddest parts of human history was you keep mentioning the Library of Alexandria, but when that got burned down,
Mhm.
and I think it was because of religious reasons, of course, but what a lost collection of knowledge and wisdom.
Mhm.
And we've been able to kind of piece things together, but talking about the dark side of human is when that thing went down.
Yeah. And I mean, like with the same thing in China 3,000 years ago when they wanted to, like, okay, we're going to burn everything, every recorded document from before today, because China's history starts now.
Right.
Well, that's the difference a little bit
Mhm.
than if you look at Chinese culture or then you look at maybe Islamic.
Mhm.
We've talked about this in the past. There was a time period, and that's much later, like 700 ADs by the time this comes along. But there was an idea that we should get rid of every competing Quranic document, and then have the more pure one. And so there was whether it was burnt or shredded or whatever, got rid of them all. Where you got in like New Testament scholarship or even Old Testament, but you're looking at the Bible that talks about, Jesus, that it's completely different, and it goes back to Egypt. That's where we found most of the Old Testament documents in the 1940s and 50s, and we're still finding more. So we have so much wealth of texts, which says, okay, it's much more broad, but that also brings a problem because it's kind of back to your Pythagorean thing. Well, I got one proof. That's good. I don't need more proofs. And well, and from an Islamic standpoint, that might be a positive thing. We just got the one thing. You don't have to worry about competing text. The good thing about the New Testament text is there's so darn many of them. The bad thing is there's so darn many of them. Now we have to, this one doesn't quite line up. And it gets a little messy. And I think giving back to your the book there with the you've got different perspectives now. Now it's a little different here because you're coming to the same. It's not a philosophical truth. It's more of a mathematical truth. But I think what as we've been doing this whole intersecting us stuff, it's just amazing to me how much I look at the world as saying everything kind of flows through spirituality. That's the way I look at it. I know you don't necessarily, and all the time. But is it that, okay, I'm right and you two are wrong, or you're right and us two are wrong? Or maybe we can look at that. Maybe they do have, there's some, let's use a Hebrew term, simultaneity, or a word means the same thing differently at the same time. And that's in math too. Could we actually have different perspectives and still stay on the same lane together a little bit?
Are you asking if our parallel lines will ever cross?
That's exactly right. Yeah, everything comes
What a
back.
segue for the listening audience. We did not plan that segue.
We actually planned nothing.
We
complete,
planned
but,
maybe a different segue, but that's a perfect segue into moving through history. And so far we've been focused on the BC part of history, and we're going to jump really quick now. Just take a quick pause at Newton. Newton was one of those guys that, of course, did mighty things. And he made a quote, though, that's often attributed to him, that if he did mighty things is because he stood on the shoulders of giants before him. And so talking about change, one of the things I've really thoroughly enjoyed was to not only see, well, what did Newton discover with calculus, but how did he discover it? And all of the works that happened before that is really cool. And so many people came like within an eyelash of discovering calculus before him. And he just kind of like got it, like he was kind of like the old Chicago Bear, the refrigerator, is like, okay, we're going to get down to the 1 foot line, and then we're going to hand it off to this 350-pound guy who plays lineman, but he's also pretty good at getting across the finish line. That's almost what Newton did, was like all the mathematicians came there, and then let's just hand it off to the fridge and get it over. And not to dismiss anything that Newton did, but he even recognizes that the ball got to the goal line, and he just got it over. So that's Newton. He got calculus going, but we're not talking about calculus today. We're talking about geometry. It's all related, of course. Let's then go from Newton.
What's the time period of Newton? Help me out.
1600s.
Okay, 15th or 17th century.
17th century, yeah.
So we just jump forward like 1700 years.
Yeah, a long time.
Wormhole.
Yeah,
like almost
around
2,000 years.
1660, I think, was when the plague hit, and he did his calculus work, and then it wasn't published till like around 30 years later.
Okay.
So it took a long time.
Yeah.
And that's the neat thing about this, is that we like things to happen instantaneous. We want our answers now. We want conflict resolved today. And that's just not the way a lot of these things have happened. And it's given me encouragement to give time and space to let truth kind of like work its way through, and not to be in a rush for it. Truth is not going to change tomorrow, so I don't need to push it. But anyway, so there's Newton, and then you've got giants like Euler. He took up like all of the 1700s, the 18th century, incredible math. And he started thinking about some things about space that were really revolutionary. And then a new guy, Gauss, came in. Carl Gauss, some people think was the greatest mathematician of all time, but he was the early 1800s. And he started to walk on hallowed ground and like question the 10 Commandments. Not the 10 Commandments, but he started questioning Euclid. And picture this, you're the greatest mathematician of all time. Your name's Carl Gauss. Everybody reveres you. Smart, accomplished. And he's starting to think about some things about geometry. And he realizes that, maybe Euclid wasn't wrong, but maybe there's more to geometry than Euclid. And so he started,
It's even simpler beginning, right? Where I think he just was like, well, I'm the greatest mathematician ever. I'm going to take up, the torch of getting rid of the fifth postulate. I'm going to prove all of Euclid. I'm going to prove the fifth postulate's true. And in math, I love this, but one of the things we've talked about are the different ways to prove things in math.
Yeah.
Right. So one thing is, if this is true, then this is true, then this is also true. But there's also this thing called proof by contradiction, where instead of assuming that the thing is true, I'm going to assume it's not true. And then I'm going to try to find something, assuming it's not true, that's unreasonable. Like, obviously, if it's not true, A does not equal A or something like that.
Correct.
Well, then my original assumption must be wrong.
Right. Yeah.
So what he does, right? So what he does is he goes, well, I'm just going to assume that the fifth postulate isn't true, that parallel lines do cross, or they don't stay the equal distant apart. And I'm going to continue deriving proofs from that postulate until I find something that contradicts itself. So it wasn't even that he was trying to prove that, there's more geometry than Euclid. It was the opposite. He was trying to prove that Euclid's geometry was the only geometry, and I can do it with one less assumption.
Right.
And that's the initiation. And so he spends enormous amounts of his life just doing proof after proof after proof, trying to find a contradiction of this non-Euclidean geometry.
Right. And he discovers that there is another geometry, but he doesn't tell anybody about it. He writes it down.
Oh.
And the reason why he doesn't tell anybody is he's afraid. He's afraid of what other people will think. So you're talking maybe the greatest mathematician of all time has this groundbreaking idea, and he's afraid to tell it. I just think that is so amazing, because how much fear still keeps us from truth today. And I don't think that, we so often think of people that are fearful as like weak. And, I'm strong enough, I can overcome fear and whatever. I think that some of us maybe have more fear than others, but I think there's always things that we're fearful about. And rather than try to deny it, I think it's good to acknowledge it and even embrace it, because Carl Gauss was afraid. And so one of the greatest discoveries he could have shared, but he chose not to. They found out after he died that he'd written about it, but it wasn't then until 1829 was when the math world discovered, this is revolutionary here, the world is not flat. We thought we knew that before, but in math,
it's still up for debate.
You're right.
Some.
In some circles. But
well, I don't know if they're circles. They're more like squares.
But up until that time, truth was flat. Geometry was Euclid, and it works great on a flat plane. But in 1829, so let's just put that in perspective, 100 years later was 1929. That was the stock market crash. And then now we're almost 100 years later.
Mm-hmm.
So not too terribly long in the whole scheme of things. There's a lot of smart people that lived from Pythagoras to Euclid to Newton to 1829. And the person who started all off, his name is Nicholas Lobachevsky, a Russian guy. And he published something in 1829 that proved that it would introduce a different geometry. And it was called a hyperbolic geometry. Mm. And if you think of like a saddle, that's what he pictured instead of a plane. A flat plane was like a saddle you'd like ride on a horse, that's what that plane could look like. Now, no one thought that was anything important or real or whatever, but he just realized if we assumed space was like a saddle, then we could get rid of the fifth postulate and replacing it with another idea that there are infinitely many parallel lines. Let's just assume that, like self-evident. Let's just pretend that. And that's all it was. It was a pretending. But the point was he could take everything else that Euclid put together, the four postulates, and then he could create a completely different geometry that was equally as correct as Euclid's. In other words, you could prove it logically, just like Euclid proved all of his theorems. And so he came up with all kinds of different results because he changed one assumption. Mm-hmm. And so that was the beginning of non-flat geometry. And he was the first one that had the courage to come up with this. And ironically, just to show you how things are always kind of like progressing together, that there's not always just this, one idea that comes out of nowhere. A couple years later, a guy by the name of Hannes Bolyai, I think I pronounced that right, Bolyai, and he's a Hungarian mathematician. And in 1832, literally 3 years later, independently, they were in different parts of the world. They didn't communicate. He came up with essentially the same thing. Mm-hmm. And so all these thousands of years, nobody did anything. And then now within 3 years, two people came up with something. And there's an interesting story with Hannes. His dad had been working with was a mathematician, and he'd been studying the parallel postulate. And it's hard for us to imagine this, but this thing is mind-boggling. And he spent his lifetime thinking about it, and it ended up causing him to go insane, literally. And when his life was ending, he was a crazy guy. And he found out his son was trying to do the same thing he was doing. And he implored him. He literally said, implored him, do not mess with the fifth postulate. Oh. It's going to make you go crazy. And I'm evidence of that. Stay away from it. This is like, it's going to, once you start really thinking about it, it's going to blow your mind and you won't be able to come back to like reality. Mm-hmm. You're going to go off in this other dimension and it's going to mess with you. Mm-hmm. And yet he did. And he independently. So that's the kind of like ideas that math has produced over time, that it took that kind of thinking, that type of dedication, and it occurred in two different countries, two different ways from two different men, but they both arrived at essentially the same thing. Mm-hmm. And that's called hyperbolic geometry. Mm.
Mm-hmm. Well, and that you think about, you were talking about your son with the why questions, which I think is, the Socratic method and all that kind of stuff. But it's almost like here in math, the thing that really had worked for people was what if. Like you go back to, I can't remember the dude's name, but the parallel thing. The what if this postulate isn't true? Let's try that. And so it's almost like the scientific method to some extent. The idea that we're going to make a hypothesis. What if this is not true, or what if this is true? And then we're going to test it, and we're going to find out. But the thing that also got me, when you were talking about his dad, because he kept doing it, and then he figured it out. But I wonder if he said, okay, maybe not even consciously, but he's kind of like, well, Dad kind of got messed up because he was going this direction. And maybe he just thought, I'm not that one. That kind of drove him bonkers, so I'm going to stay away from that particular way of doing it. So I guess my point is, he learned from his elders how not to do this, and maybe he was maybe not as psychologically unstable. I don't know, but I think again it's that I see that so much in definitely in philosophy, with Plato, certainly Socrates before him, the what ifs. Plato's idea of forms, what if there is these non-physical forms that are perfect, and it's a postulate. It's pretty darn hard to prove, but he believed it. It was a faith proposition. And I think, who would think that math had faith propositions? That's kind of what you're doing. You're saying, well, I'm going to trust that these parallel lines are going to touch eventually. I don't know that they do. But then we're going to test it and see how it works in at least the real world of math and all those types of things. And so to me, that crosses over so well. It's like, I don't know why I thought of this, but it's because I'm a theological geek. But, what we call the doctrine of the Trinity for Christians, which is really hard to get your mind around. I'm still working on it. Everybody probably is. But what if this God is one being, but in three persons, which just doesn't, mathematically really set good. And, we were taught in seminary that every time you made a proposition about the Trinity, you were a heretic, because you just can't get your mind around it. But it still could be true. And it's kind of like, can we prove that infinite lines will eventually touch? Well, it's hard to get there, and prove it conceptually. And I think that crosses over. And I guess maybe you guys can speak to this from the way you look at things. Is it possible in math that we can believe or prove something's true without having a complete conception of all of it? Does that make sense?
Well, yeah. So I want to just, a postulate's an assumption.
Right. It is.
So inherently, it's not so much that we're trying to, the goal that they were trying to do was prove one of Euclid's postulates. And if you can prove something is true from a deeper truth, then, it's no longer an assumption. You've proved it to be true.
No, it's a proof. Yeah.
So we get it out. So now there's only 4 postulates. That was the goal.
Yeah. But instead, what we find out is that, parallel lines don't have to remain equidistant apart. They can touch if they're on non-flat planes, or they can get further apart if they're
or they can go
planes.
Like
they can change their distance.
Don't stay as the same distance apart.
The Cartesian plane is flat, and all of a sudden if you warp it, you introduce additional dimension and to it. So your question of like, can we know something without knowing everything? I think the answer is yes, as long as we connect our base assumptions back. Here is what we're assuming.
Okay.
We can move forward from there. Like let's take Euclid as a great example, right? So you're reading the Elements, the first, 5 postulates, the first proposition, right? That first proposition is true, even if you don't know anything else about math, right? You literally don't have to know anything else. But as long as these assumptions are true, this first proposition is always going to be true as a result. And I think in the pursuit of truth, it's a mix between evaluating what your postulates are. What are the assumptions you're coming in with? Can you prove that they are true or aren't true, which will, break everything down after, but then you just have to get to a point where you're like, okay, I just accept these as my postulates.
Okay.
And then you move forward from there and go, okay, if we accept these as truth, if we on faith accept these, what are the things that their implications? And then you work to prove things from them. But it's almost a two-factor of challenging the assumptions you come in with, which is what created the whole non-Euclidean geometry field. But then the rest of math is like, you have to move on eventually and just accept whatever the postulates are. And then you can just follow that chain of logic down and discover new things.
And I think,
which is kind of what they did in the trigonomic explanation of Pythagoras. They're like, we're just going to, again, they try to say, we're going to take a postulate out and we're going to see if we can still prove this in a trigonomic proof.
And another kind of like in-between step would be a conjecture. So a conjecture is someone who says they think something's true, but they're not proving it. And so that's common in math too, is someone kind of like sees all the dots, they're pretty sure it's true, but they can't prove it, but they're going to conjecture. And then some time down the road, someone else will either prove it true or not true.
Okay.
So one of the most famous conjectures out there now is the Riemann hypothesis. And we're going to get to Riemann in a moment. But his hypothesis was stated in 1859. And so much of math has been built on that conjecture, but it still has not been proven.
Dave, who is Riemann?
Bernard Riemann, a mathematician. So we talked about how like relationships matter and things in history happen very interesting. And Riemann grew up as a poor man in a Christian, very devout Christian family, simple-minded, and his plan was to become a theologian because that's what his family was expecting him to do. That's what devout Christians
And where
did.
was he? Where did he go?
I believe he was Germany.
Germany. Okay.
I should know that. Don't quote me on that, but I think he was Germany. But then he got to school and people said, this guy's really good with math. Can he, change his major to math?
Can he be useful?
We think he might.
Stuff.
And so he was able to change his major to math. And he happened to run into a guy that was pretty good at math named Carl Gauss.
Oh, okay.
So he was mentored by Carl Gauss, influenced. So all those ideas that Gauss had about non-Euclidean geometry and afraid to publish, here's Riemann as his mentoree. I mean, talking about two great giants at the same time, one learning from each other, discipleship. What an amazing thing where would math be if that relationship didn't occur?
Yeah.
And so just a shout out for the ability to mentor others and be mentored. What a great thing. I know all of us, we've been mentored and we mentor others. It's just fantastic. But this is one of those things in math that literally changed the world. So that's who Riemann was. And, he came up with this hypothesis, the Riemann hypothesis, which we're not going to get into, but all of internet security is really based on it. There's literally thousands of mathematical proofs that are based on it being true, but it has not yet proven to be true. So if it's proven to be false, then there's going to be this domino effect of things, really bad things happening.
Okay. Which is one of the things I was thinking of, because you're gonna, if you do have one of these things that you assume is true, but you haven't proven is true, and then you find out later it's false, you got to go back and redo.
Yes.
Right.
And I think that's, but it's interesting. I wonder the psychology of those two, and I get the names right. Gauss was fearful.
Yes.
But he was it seemed like he was thinking in the way that I'm going to say this is true and prove this, which is going to make people upset. Where Riemann is more like, well, let's just assume it. What if this is true? I'm not really making it. And so it doesn't become as fearful for people.
Well, I think Gauss was, as this prolific mathematician, was trying to remove the fifth postulate. So the fact that he couldn't was like, well, I don't want to tell anyone I can't.
Right. Yeah.
And I think Riemann kind of looked at it and was like, well, what if there's a whole new field of math here? And Gauss was like, okay, well, I've gotten this far into it.
Mhm.
You're going to tell me this is a whole field of mathematics.
Mhm.
I just couldn't solve the problem,
Mhm.
right? Because that's his original purpose, was to solve. I want to find the contradiction,
Yeah.
so that I can
Mhm.
be right and
Yeah.
I can be done.
Mhm.
And Riemann says, no, there's a whole new world to be explored. And there's another point I want to bring up that's really fascinating. I was reading recently about just the culture of higher education.
Mhm.
This idea of these PhDs, these people becoming experts, and then mentoring the next generation, and them that reflecting back, right? Like, okay, the people I take as my graduate students, the people I'm going to train as my PhD, their legacy is reflected on mine. So it's just as important for me to train and build. And that relationship, I think, is really why we're having this conversation
Mhm.
of like, I am discussing and challenging myself. That's why PhD dissertations are challenging, right? I
Mhm.
have to go to a bunch of experts
Yeah.
and they have to prod and push and really figure out if I have done my work and I've made the right assumptions, I've made the right logical conclusions, I've run the right tests. And it's not until you're in that environment of being really challenged that you can discover them, that you become affirmed that those truths are real.
Mhm.
Right. And it's not until you've had those conversations with people that maybe believe different or have a different background that you can find truth.
Mhm.
Right. Discovering it on your own in a notebook doing math proofs is good, but until you send it around to your friends
Mhm.
and say, am I onto something?
I think that's very insightful,
It
because
is.
it does come down to the
Mhm.
the religious point of it, because so many folks, in that would have a similar worldview, we just kind of say in kind of our own little sectarian groups, and we don't get challenged. It's kind of back to, we're almost fearful of being challenged, because what if what I believe isn't true? Then then I got to go back. I got to restart, because if I'm really looking for truth, and this is an error, okay, I got to, but it's back to what you were saying with your PhD stuff. If it's never tested, how do I know it really is strong? A faith or proof or whatever, truth, or whatever we want to use. If it's never tested, if it's just assumed, but I can't really give you any evidence for it, then it's not really all that useful. And that's where I think this comes back, because I think, in the way you were talking about, Dave, the idea of taking Euclid and you too, Charlie, adding to it, not changing it. It goes kind of back to the Paul thing again. It's like he was trying to prove that this was wrong. Instead, and he was looking at it that you had the Torah was this, and then this Jesus movement was here. And what he finally realizes is it was built upon that.
Right. Yeah, exactly.
Yeah.
What a revelation
Euclid
that had
versus,
to be.
it's
Right.
got some similarities there.
It does.
That it may be a lot, and maybe that's why we talk past each other just in life, in normal life, because we're trying to think, well, I'm here and you're here.
Right.
But maybe there is, can we find this?
Yeah.
Can we
and
find
build
the
on each
Euclid?
other.
And then whether you're in whatever worldview you have, and then, okay, we're building on it. I'm not saying, get wishy-washy. We all believe the same thing. We don't. I realize that. But again, can we have conversations that are meaningful and purposeful to try to find truth? Because we're looking at it in a perspective and being respectful to what's already, okay, we know this. We know suffering exists.
Yeah.
Okay, we got that. Okay, now what are we going to do with that?
Right.
How do the different worldviews deal with that? And are some of them, how do they cross over, and all those types of things? Just one example, but yeah, looking at this history, it's like, it's interesting how what worked was the what if questions, not that I'm going to prove it wrong questions necessarily, and how can I build on, as you put it, the shoulders of those who've already done a lot of the work. Because, again, Christianity, Islam's that way too, builds on what had come before, and I think that is such a cool parallel historically into these things. And,
right.
We can learn a lot from that in our today, because we got so many sectarian, especially in America. It's like the politics is just so annoying because we can't talk to each other.
Right.
Right. Just come on, lighten up a little bit.
Okay, so let's take a quick recap where we're gone. We start out with foundational truth. So that would be the 5 postulates. We built a flat truth, which was Euclidean geometry, and then trigonometry on the side. But then we realized trigonometry and geometry are separate and yet related, which is really a cool thing. And now we've got the introduction to non-Euclidean geometry called hyperbolic geometry, done by Nicholas Lobachevsky and Hannes Bolyai. If I keep saying them, I may get it better each time. If you are great descendants of these people and I'm mispronouncing their names, my apologies. And that's not the end of it, because now we are going back to Riemann, and he also came up with a different kind of non-Euclidean geometry called elliptical geometry. And his idea was that parallel lines intersect at 2 points. And if you think of parallel lines, it doesn't seem to make sense, and it seems really ridiculous until you think about something like the globe. And picture you and your friend both of you at the equator, and you both go north at 90 degrees to the equator. You're both perpendicular to the equator, and so you're parallel to yourself, to each other in Euclidean geometry, because 2 lines that are perpendicular to the same line are parallel to each other, and therefore they would never meet. But if you looked at your globe lately, those 2 lines do meet at the North and South Pole. And so that's a picture of Riemann's elliptical geometry that talks about those are parallel lines, and they meet at 2 spots, the North Pole and the South Pole. And so that is the second part of what we're calling the round truth. Hyperbolic geometry and elliptical geometry all occurred about the same time. Riemann's was in 1854, and his became more famous because then of what occurred after that. But I don't know, I'll pause here for a moment to see if you guys have any thoughts on the hyperbolic geometry.
Well, I always
elliptical geometry, yeah.
Well, I mean, my first thought was it's almost, I know we'll get there later. We talked about it a little bit, the idea of space-time curving. You know, if you're not, the lines aren't curving necessarily, but the space that they occupy is.
Right. Yeah, I think one of the interesting points here is this is a point of inversion in math.
It is.
When you go back to Euclid and proving geometry, the Pythagorean theorem, these are extremely practical forms of math, right? Like, I can translate the area of one object to another. I mean, it helps with building buildings and carving stones, and how from very simple tools can I get very precise measurements and precise shapes. Even the emergence of calculus, right? Isaac Newton was using this to help derive the path and motion of objects. This is like an extremely practical form of mathematics. But when we get to Gauss and to Riemann, what we really start to see for the first time is math that isn't connected to reality, right? In a practical way. These are just, we're following this logical set of assumptions and their results, and discovering new parts of mathematics that really just exist conceptually.
Correct.
They exist in our mind. There's no practical real world. I mean, the globe is a good example in one, but we can come up with, infinitely many shapes of planes that are hyperbolic or elliptical, curved down or curved up. And there's no use. But we get to explore it.
That's
we
right.
get to discover.
Yeah. So this was extremely important in the math world, and I'm sure no one else cared a hoot about it because it's just math theory, it's research. And like so many people think of math research, it's like, oh, tell me, is this going to cure cancer? Like, is it going to help my children get healthy, or is it going to pay my bills? No. Well, then, you guys go ahead and do your thing, but it's really not important. So this is the category of importance this had outside of the math world. And it took a long time. One thing is they didn't have like the internet. It took a long time for people to actually read these things and then to pass them on. So, but once it got going, it was like a wildfire in the world of math, and they started building things on it. And it's kind of like now they felt free that we can actually go outside of Euclid. This is amazing. But, it's all theoretical. But it was like a fantastic flourishing of math ideas. And there's so many great mathematicians after that time that just took that and built upon really great math. But it was all theoretical until the 20th century turned. And we have a new person that entered the story. Who wants to introduce our new character?
Dun, dun, dun. Is it 1905?
Yeah.
Yeah. Albert?
Albert.
Yeah.
Yeah.
Not Albert Pujols.
No, not Albert Pujols.
Albert the Pujols. It's very, just like Alexander the Great, Winnie the Pooh. But yeah, Einstein, it was 1905 when he did this general theory, right? Or is it specific or special?
I get it all mixed up, to tell you the truth.
Mhm.
But anyway,
for.
he was working on his theory of relativity, and he had all the things in his mind the way he thought it should work, but he was trying to do the math and it didn't work. But he was using the math of Euclid, because that's
It's really interesting because you talk about like conjectures and truth and proof. So really what Einstein did is he made a set of conjectures around how objects should behave when either they're going really, really fast or they're really, really heavy. And based on these conjectures, he had these, again, no experience, right? He's not sending things at the speed of light and then measuring their
They didn't
results.
have computers back then.
He's a patent clerk and he's riding his bike home and he's just thinking about, like,
he's not a world-known physicist. He's just Joe Nobody.
Yeah, and if I move on a train, and it's going really fast, and if two objects move next to each other, then like how does that affect their perceptions of time? And he has this idea that gravity, that the very fabric of space and time are connected.
Correct.
And through this idea of connectivity between these two, he comes up with this idea that, well, maybe gravity is not a force that's exerted, but really just a manifestation of the shape of the universe.
Right.
And again, no proof. No, there's no math behind it. And so he instead has to work backwards and go, okay, well, I believe this. I conjecture for some reason. And when I think through some of my assumptions that are too far up, my postulates are too far, I need to derive them backwards. So he has to go and learn the math behind it.
And he wasn't a great mathematician, but he had a great mathematician as kind of like in his office or whatever. And so whenever he needed math, he would just go to his friend and say, hey, I'm stuck here. Help me out with the math. And so this was one of those times where he was stuck and the math didn't work. And so this guy said, well, you're right. This is not going to work. But, there's this another geometry out there that's kind of like nobody really knows anything about. And it seemed like it's really crazy idea. But, let's just give this some thought. Let's give this some ideas. And I'm going to play with this a little bit. And so that was when he was using the elliptical geometry from Riemann. And so they took that math from Riemann, and then all those equations that didn't work just magically worked. I mean, if you can imagine like Einstein, that aha moment, because like you say, in his mind, he believes it's true. The physics, how he thinks space works, like this is reality, but the math wasn't there. And so like, how does this work? And then to find out that there's this old idea from 60 years back, and this 1854 guy that was probably didn't even know what a car was or electricity was, and all he did was sit around and do math, came up with this idea, and now this is the idea I need. That had to be so cool.
Yeah, it was an epiphany, to have something like that. And I think that's what, again, it's just building on the next thing, building on the next thing. And I think that's so true in life, where you think you're doing something that seems to have some meaning, and then it might be your kids that use it. It may not have any practical use for you, but it ends up being used by, and I suppose Riemann probably didn't know that, but I think that it just kind of imposes itself. One of the things that I thought was interesting, and I don't know if we want to talk about this if it's too much of a rabbit trail, but you use the word that he discovered calculus, or he discovered. It's different than created or invented. Maybe it's a better word. He didn't, because I've heard people say, well, Newton invented, or Einstein invented, or whoever, I don't know what the guy's name that did the math that helped him, but discovered, which is essentially making an assumption that it's already there. It's just that which I'm sorry, but it brings me back to Plato again. There's a perfect form of the relative geometry or whatever we call it. We just haven't discovered it yet. It's there, but and that's such a cool part about math. That's not like physics. It's similar, but
it's there, and yet it's and yet there's like conjectures,
right,
and things like that.
There's methods to use to try to get to it,
right?
And we've talked about some of those.
Yeah,
right.
Math is the language of physics.
Yes,
right.
it is.
It's how you explain physics.
Right.
Yep.
Yeah. In fact, I read something that talked about what a revolutionary thing this was that Riemann didn't just give the math to the geometry that Einstein needed. He gave the language that it needed.
Okay.
And so don't think of it as just equations, that we're talking about space-time, how the fabric of the universe is. There was no language that could talk about that in an objectable way, other than, you and I could maybe do some sci-fi thing, wishy-washy talking about it, but that's not really consistent. And that's what, even though Riemann didn't have an application for it, he developed not just the math, but the language about it, so that anyone that would read it could see this world that he built out of nothing, in his mind. He built this world in his mind and gave it a language that a physicist could come in and say, oh, that's speaking my, I can understand that. And so I think that's really cool.
So he's translating. He's essentially translating, I was thinking language. He's translating an idea that nobody into language that now we can interact with and in some ways understand.
Like, he came up with new terms, which I don't know too much about, like tensors. If you're a physics math person, that's a big thing for you. Well, there was no tensor, before.
Yeah.
And so, like, what is that? Well, that wasn't something that was just talked about. Riemann's the one that came up with kind of like those words that really was the foundation for Einstein.
Yeah, like integrals and derivatives in calculus, right?
Right.
You have to, it's not just this idea that you can, translate between different algebraic formulas. It's the notation behind it, right? It's the language you communicate in, right? Like, it's almost impressive that Euclid got as far as he did and the mathematicians did, because they didn't have algebraic notation.
Correct.
Right. And
That's
then we
amazing.
discovered algebraic. We created. We didn't
create-
even discover it.
We create notation.
Yes, we create notation. We created algebraic notation. We created the Cartesian plane.
Right.
Right. And it's in these creations that these sandboxes that we got to, it helped us discover more of the mathematical truth that existed.
Right.
And what's even cooler, so you're Einstein, right? Like, okay, well, I have this conjecture, and then I move my postulates further and further back until basically, I guess if I think about it, back to the 5 postulates of Euclid, but just we're flipping the 5th one.
Yeah.
It's just there's still a 5th postulate. It's just
different.
It's just different,
right?
Well, good thing it's a good thing that it was there to change.
Yeah, and so now you're like, okay, I have this theory and I have the math behind it, but I don't have a shred of evidence that it's true.
So can you talk about that?
Yeah.
Like, what are some things how that happened?
So the next thing you have to do, right, is, okay, I believe this truth is real. I have these assumptions. Is there a way I can test it? Right. And again, when you think about like Euclid and this older form of geometry, the testing was relatively good, because you could go out there, you could cut stones, you could create things like, boom,
pyramids. And,
3,
that's
4,
the right
5.
triangle. I made it.
Yeah. The Egyptians, they used rope. 3 that way, 4 that way, 5 that way, and it
boom. Yeah, you're good.
Yeah.
And so, and then as you get further and further along, it's like, okay, well, I have this idea and I think I've proved it logically, but how do I test it? And so Einstein provided this platform that not only is all of his assumptions around general relativity true, but it was a validation of all of Riemann's mathematics too.
Correct.
Of like, does it propagate in real life in a way that's consistent and mathematically equivalent to the assumptions made? And so during a solar eclipse, when the moon blocked out the sun, they looked at the stars and they could see that the stars were shifted, because as the light comes around the sun, the gravity from the sun moved the photons in. So that was the first time you were like, oh wow, the fabric's warped. And then the next one was around time dilation, this idea that objects, time goes by differently when you're closer to massive objects. And so Mercury's orbit is elliptical. And so one part of its orbit, it's much closer to the sun than another part. And so because of that time, the time that goes by changes between its furthest and its closest point. And so instead of having a consistent orbit, it processes, it moves a little bit each time it goes around. And when they measured that shift, it matched up with all of the predictions and formulas that Einstein had. And so in his lifetime, early, I want to say it's in the 20s.
Okay.
Right? So very early in his, so, you know, he came up with 1920s, and not in Einstein, maybe Einstein was 30 then, but came up with an idea, created conjecture, you know, used math to evaluate and come to an original postulate, and then made predictions that were affirmed to be true.
Right.
And I think that process of collaboration, of evaluation, is really just such a great example of how you find deeper and more important truths.
Yeah, I think that's so fantastic. I just love that story. I don't think this podcast would be complete if I didn't like challenge you guys with a math question. You know, one I know it. Off script.
I'm a theologian. Remember that.
I didn't warn these guys about it. Okay, if we're in the Cartesian coordinate system and you have 2 points, what is the shortest distance between those 2 points? It's not a trick question.
Line.
Straight line. Okay. If you have 2 points on the globe, what is the shortest distance between those 2 points on the surface?
You have to stay on the surface?
You have to stay on the surface.
No, because it's a straight line.
Yeah.
We'll just dig a hole.
The circumference, or what would you call that? Come on, Charlie, you're the math guy.
Well, I was trying to think of, is there a shortest line? But I
That's a good question.
Yeah, I think there is. Or maybe there's more than, maybe there's 2.
Because you could go like this, or you could go like this, but this would be the short. Or is it the same? It would depend if it was a perfect circle, I guess. We're assuming perfect circle.
Assuming a perfect sphere.
There is one shortest distance.
There is one shortest distance.
Any 2 points on the globe.
Yeah.
This is what I'm thinking here.
Yeah.
This is kind of like me winging it too, so
yeah,
I could miss something, but I'm pretty sure I'm right on this.
Yeah, well, I'm sure there's like maybe 2 points that are on perfectly opposite sides, and there's infinitely many. But aside from that, subset.
So it has a name?
It does.
Yeah.
First, what's the shape? What do you think the shape would be?
There's an arc.
Yeah, I mean,
yeah.
And what would be like the perfect arc?
Oh, well, it's got to be
circle.
Bingo.
Yeah.
What kind of circle? Have you heard of a different type of circle, maybe?
Unit circle?
No.
That's the only type of circle I know.
Yeah.
This is back to Alexandria. The Great Circle.
The Great Circle.
Have you ever heard of the Great Circle?
Uh-huh.
So basically, the Great Circle is just a circle on the sphere. And so which lines go parallel to the equator? Is that longitude or is that latitude? I always
That's
forget.
latitude.
Latitude. Yeah. Okay. So there's only one great circle that goes along the latitudes, and then that would be the equator.
Okay.
All of the ones that go through the North and South Pole, those are great circles. But if you have, let's say, somewhere, to pick 2 points, then you just draw a circle around, kind of like the equator. You just kind of like flip it a little bit.
Right, yeah.
And so that's the shortest distance between any 2 points on the globe. And it's with a great circle that essentially just goes, all the way around symmetrically, kind of cuts it in half.
Okay.
And so if you've ever seen, like, on the airplane and you're wondering, like, why are we
going over Greenland?
Yeah. And if you're looking at a flat map, it's not looking like, why are we going so far away? Yeah. It's because you're not looking at it on the globe.
Okay.
And if on the globe, if you drew a great circle through there, then that's why, unless he's changing because of wind or whatever, but generally that's what they do. And it always looks weird because they'll show it to you on a map. You're looking at it on your screen, like, why are we going this way? But I think it's so funny. Like, this is like,
it's a perception.
It's a perception thing. So a circle is, if you think about a circle, amongst other things, we think of like a circle in spheres, but that's actually the shortest distance between 2 points on the sphere is a circle. And
Yeah,
so
yeah.
I just read about that in a book this week. It's like,
Mhm.
I never thought about a circle that way. Just like we think of a straight line is the shortest distance between 2 points on the
Mhm.
plane. So that's just one more thing a circle is.
Well, I think this is true. This is from a physicist, so I don't know if you can blame him, but the idea that if you anywhere on the globe, if so, you can go like between the North and the South Pole, and then you go straight through,
Mhm.
assuming that the mass isn't stopping you, just the distance. And you go over here, and it's much shorter distance, but it takes you the same time to get through it.
Mhm.
No matter where you are, it's the exact same time.
Mhm.
And it's because of Einstein's equations that the gravitational pull, is weaker over here than it is over here. So you go actually faster. So it takes the same amount of time to get from the North Pole to South Pole as it take to get, through, Iowa down through, I don't know what's down there, but, Bolivia, even though it's much, much shorter distance because of Einstein's equations. It's
Right.
I think that was Neil deGrasse Tyson, so if you can get mad at him if he was wrong.
I wonder if that's back to Kepler's method of equated time as the planets revolve around the sun, that the amount of area that they go is the same. And so as you go further away, if you want to figure out like how far are we going to go in a day, you just calculate the area of that little sector there.
Right. I think it's similar.
It's going to be an equal area, equal distance, equal time type of thing. And so, I mean, that's, that comes from Kepler's law. So, but I think that's pretty cool.
Yeah. I think it is too. But I think it's interesting because all of this stuff, our premise is always going back to the fact that the reason we're finding meaning and wonder is because you're looking for what is true. I think that's, all these guys, whether they're theologians or generals or, it's the truth stuff that you're looking for.
Right.
Because, philosophically, that's always the hard part. It's like, I think we were talking about that on a couple of days ago about, what is truth, and obviously there's different philosophical ways of it's what's not false. I know that, that's one thing. And I think that seems to be the thread between math, science, and I think religion.
Right.
What is true? They're different propositions. I realize that because they have different purposes,
Right.
But it's still the same question.
Right.
What is truth?
Right.
And how could you know what is true if you don't understand people in history that have tried to ponder that themselves? Right. If we start from zero,
right? Yeah.
Good luck. Yeah, you got to go on the shoulders.
Right.
And I just wonder what's the next? In math, science, religion.
Right. So let's kind of recap where we're at. That's a good question to kind of like land our plane here. So we started with the foundation. We went to the flat truth, Euclidean geometry, trigonometry. Then we went to non-Euclidean geometry and found circular truth. Let's end up with practical truth. So practical truth is how does all of this matter to us today? If you're not a physicist, and I think the one thing that impacts me, I'm not a physicist, is that I get lost really easily, and I've got to rely on my smartphone to help me get from point A to point B. And the technology behind my smartphone is the GPS system. So how does the GPS system, which seems totally different kind of a concept than what we've talked about, how is that impacted? Do you guys know much about that?
Well, because satellites are further from Earth, they experience time at a slightly slower pace. So clocks are important when establishing location. And so we have to make adjustments in the clocks in satellites to make sure that they know where we are and we know where they are.
So we've got distance and we've got time to worry about. And
mass.
And math. So we want the straightest distance between 2 points. And so somewhere someone's have to doing the math on this to figure it out. Do you suppose that they're using Euclidean geometry to do this? Or what do you think the kind of geometry they're using?
They're probably using Euclidean because it's a straight. No, they'll assume everything's straight. Would they use non-Euclidean? Is there enough curvature between us and them? I don't know.
I think it has to be because of the relativity stuff.
Yeah, right. And so I think that when first did GPS, they actually used Euclidean, but it can like get you close, but close like in the matter of I'm here, but my GPS system says I'm a block away or 2 blocks away, to the point where it's not useful, really that useful. And so they're using the elliptical geometry that came from Riemann, and that was used by Einstein. And so all of this theoretical knowledge now has turned into extremely practical knowledge where we can rely upon our GPS system. So GPS is using math, and it's using, the detail math that we're talking about here that has been passed on from generation to generation, that started way back in Alexandria.
Yeah.
And it's come this far. And I don't know, I just think that that's so cool that we don't think about those things now, because we just want to make sure our GPS system works. But that shows me the power of math is that no one foresaw that talking about the parallel postulate and trying to get rid of it. That was like a house cleaning thing in the world of mathematicians that no one else cared about, quite honestly. Like it bothered mathematicians, and no one else could care less about it. But because they were willing to start probing, asking questions, we now benefit from that with an accurate GPS system. How cool is that?
Well, and I think when we talk about how everybody over time, people build on the next thing. And so it starts to make me think, okay, what's the next thing? So somebody, I might not be too old. You might still be young enough. You're way too old. But who's going to make the next, and what would it look like? And I think we may have talked about it before. One of the things I think, when you get into the time part of things, I drove from Hampton, Iowa. It took me about an hour and a half. You drove from Madison. I don't know how long that is, but it wasn't instantaneous.
Yeah.
But that seems to be, to me, maybe the next, I don't know, conceptually, how can, the Star Trek thing, how can we get from point A to point B by converting mass into energy and then back to mass, the teleporter. And then so we could be anywhere we want to be fairly quickly, and is the math there? I don't, you guys would probably know, maybe there is some math there that can work, because you get, equals MC squared, maybe where mass gets converted to energy, because boy, if we can come up with that. I mean,
I just saw a Sherlock Holmes show last night, and it happened there with the chocolate bar.
Well, there you go. Well, Willy Wonka did it too, I think, if you want to go there. But I again, kind of back to what we were this is the idea, we want to, amongst ourselves, but then the people listening and interacting with, where can we go next? Or can we perfect GPS even more? I mean, whatever. Maybe we can do better with the elliptical stuff, But there's more to be discovered out there that will practically help people's lives, But we have to trust it. If you're a block away, you're not going to have a self-driving car, because you're going to run into each other every 5 seconds. But if you can get within millimeters, a couple millimeters right, well, then you can have, the lane's wide enough. You can have self-driving cars with GPS technology, because we trust it. I remember, I think it was Scotty in Star Trek. He would never want to get into, or no, it was Bones, the doctor. He never wanted to get into those teleporters. He's like, you're taking somebody's mass and turning it into energy, then back into mass. I don't like this voodoo or whatever, And even though he understood it worked, there was still some fear there. And I think maybe that's one of the next things that, mathematicians can work on. If you wanted an assignment. But again, it's good. The only way you're going to do that is you're going to have to build on what's already there, and you're going to have to wonder if is it true that we can do this, even on quote paper. I think that's something that it would be kind of fun to see if we can do.
And importantly, you'll have to discuss it and be challenged
Yeah.
continuously to find that the deeper the truth. To make sure to validate everything that you built on.
And that does cross over into the philosophical things and the theological things and those things, that because it all comes down to meaning and purpose, right? What difference does it make if it's true if it doesn't have any meaning or doesn't have any purpose, ultimately, so I think that it's kind of cool the way they cross over.
So do you have anything that you want to like encourage our audience to think about for their own lives? What would, if you were them, what would you encourage them? Most of them are probably younger, and what would you want them to be thinking about? Like if you were back at their age or whatever, any thoughts that you want to challenge them with?
I don't know if there's a specific thought I'd want them to challenge them with, but you have to talk to people who believe differently than you, and you have to be open-minded that your beliefs might be wrong. To ignore either of those two things is to you're almost guaranteed to avoid or miss a lot of truth. But when you discuss with people who have different postulates, conjectures, proofs, you understand a lot more about the world, and inevitably there are going to be assumptions you have that are wrong about anything, and deriving them on your own is a lot more challenging than having open conversations and listening to other people's. We live in a world that is very echo chamber centric, and so it's not something that's going to come naturally, this interaction, and it's not always going to be comfortable either. And so being uncomfortable and being intentional will help you find deeper truths in life.
Yeah. And people like Carl Gauss, were the same thing, and they're a lot smarter than us. So those feelings, don't feel bad about them, and don't pretend like they're not there. That's naturally, but then still, how can we move forward? And if no one shared these ideas, then we would all be in the dark, literally. And so people, the next generation, depend upon, I know our listening audience has a ton of great ideas and thoughts, but they need to get them out of their head and into someone else,
into some conversations,
conversations,
and especially with people that, because we all, our worldview is somewhat similar. Yours is a little different, but it's been so helpful for, I think, all of us to do that. And I think coming off of yours, I would just challenge people to, especially people of faith, and that could include agnostic. I'm pretty real trustworthy that there isn't something more than this. Is the idea, don't be so worried about being certain about your beliefs, but it's okay to be confident. And looking at it from a math perspective, if I'm certain, I'm kind of saying I'm 100% sure this is true, which is almost more of a psychological thing than it is a evidential thing. But for instance, I could say, well, I think the Bible is true. I'm confident of that. Certainty would take me to more of a psychological view of it too, but with the evidence. But if I can come to it and talk to Charlie and say, okay, I'm pretty confident this is true, but I'm willing to say that obviously, if I'm only confident, there's a possibility that I'm wrong. It doesn't mean I don't see it as trustworthy, that I don't use it in my life. And that's what people do. They think, well, if I give up my certainty, then everything, all the dominoes fall.
Then it can't be useful.
It can't be useful.
But that's not true.
But that's not that. We don't do that in anything. Even GPS. Are we 100% sure? Well, you're getting close, but there's still probably more confidence than certainty there. And I think certainty is an emotional quality, really. And so I just encourage people, you can be confident in what you believe, what you think is true, but you can still talk to people that are confident that you're wrong.
Right.
And not be emotionally, just completely obliterated by that. And I think that's what allows us to have real conversations. Because I'm not just saying, well, I'm going to set aside my certainty. I'm really certain, but I'm going to set it aside and fake it so I can have a conversation with you. I don't do it that way. I'm confident, but that's somewhere less than 100%. And it opens up the conversation to have in a real way and maybe in a true way.
Right. And what I like about this story is that, I think truth is something that's out there that can often be scared upon because people have been handed truth down in a way where they were not asked to question it. There was no space for them to bring doubts into it. And as a result, if someone even mentions the idea of something about truth, it can cause an emotional reaction, thinking that, okay, I'm being handed down something that I'm not even allowed to question. And I just think that that's very damaging place to be at. And for me, what's really helpful is to see truth as really kindness. And so as I seek truth, I'm seeking, because I believe that there's kindness behind the truth. And so for me to seek it, I'm seeking kindness. And so if you're seeking kindness, you're not afraid of it. You want more of it. But it does mean that sometimes you need to adjust. You need to, like, but that's okay if you want. It's like, okay, well, I'm getting closer to a truer kindness. Well, I want that. I don't want to be like less kind. And so if anything else, I want to encourage people to kind of view the truth as something that they can explore, that they can share, and other people benefit from it, and we benefit from other people. Ironically, if you think about a GPS system, one satellite doesn't bring truth. At least 4 is, I think, the goal, and the more, the better. And so, I look at these two guys, Charlie and Brian, as 2 of my satellites helping me navigate where I'm going in life. And so find people that you can also have in your life that, real relationships that you can talk about tougher things together. And I think that will be a way to, you can benefit from them, and then they can benefit from you.